Welcome to The Explainer. Okay, today we are unpacking what might seriously be one of the most monumental scientific breakthroughs in human history. NASA's Perseverance rover has been meticulously exploring the Martian surface, right? Well, it just stumbled upon something that literally has the entire astrobiological community holding its breath. We are looking at the very real possibility of ancient alien life.
So, did we just find life on Mars? The short answer is, we might have. Scientists have found what could very well be the actual physical remains of ancient Martian microbes. Over the next few minutes, you and I are going to act as cosmic detectives. We're going to look at the clues, analyze the chemical fingerprints left behind on the Martian surface, and figure out exactly what this jaw-dropping discovery means for our understanding of the universe.
And the excitement is incredibly real. Take it from Dr. Ed Cloudis, a key scientist behind this discovery. He pointed out the specific detection of organic molecules. And in the world of astrobiology, organic molecules are a massive deal. They are the literal building blocks of biology. Finding them on another planet is like a flashing neon sign for possible life, and it completely validates the sheer excitement surrounding these specific samples.
Let's get right into the Jezero crater discovery and follow the Perseverance rover.
So while rolling through a dried-up ancient river delta known as Neret Favalis, Perseverance captured something pretty strange in the sedimentary rocks. Scientists are calling them leopard spots, these tiny, colorful rings. This brings us to a really critical concept, biosignatures. A biosignature is essentially a fossilized chemical fingerprint. It's an assemblage of minerals that gives us hard evidence of life. So the million-dollar question we're asking is, are these leopard spots the actual biological signatures of alien organisms?
Moving on to decoding the leopard spots and the chemistry of ancient life. Here is where it gets crazy. The smoking gun lies hidden right inside these leopard spots. The rover detected the signatures of two highly specific iron-rich minerals, vivianite and greigite. Now, why does this matter so much? Because here on Earth, whenever we find this exact combination of vivianite and greigite paired up with organic molecules, it is inevitably, absolutely always, associated with biology. Microbes actually interact with iron to generate their energy, and they leave these exact minerals behind as waste. It is a textbook biosignature.
Which takes us to Mars, the ancient water world of 3.5 billion years ago.
Now, looking at the freezing, arid red desert of Mars today, you're probably wondering, how could microbes ever survive there in the first place? Well, to understand that, we've got to flashback billions of years. By mapping out the Martian eras from the pre-Noatian all the way to the current Amazonian period, this stunning picture emerges. Think about this. 4.5 billion years ago, a massive ocean covered a third of the planet. By 3.7 billion years ago, it was literally the perfect environment for early Martians. Mars wasn't just capable of supporting life, it was a prime location for life to take hold, even before Earth fully kicked off its own primitive biological chain reaction.
During this ancient Noachian period, the planet was essentially a watery paradise. It had a dense atmosphere, trapping heat through a greenhouse effect, fueled by all this widespread volcanic activity. But the most fascinating detail? The acid rain. As this acidic rain fell, it dissolved the Martian rocks, which released vital minerals and nutrients directly into the rivers and lakes. It acted like a free chemical buffet, delivering essential food right to any single-celled organisms just trying to survive in those waters.
Next up is the tragic atmospheric collapse, or how Mars died.
Sadly, somewhere between 4.1 and 3.7 billion years ago, things went terribly, tragically downhill. The complex physics of this planetary death actually started deep underground. Mars's interior cooled off, and when the core cooled, the planet's protective magnetic field completely dissipated. Without that shield, solar winds, which are just streams of charged particles from the sun, slammed directly into the Martian air molecules. This ionized the atmosphere and literally knocked the planet's air out into the dark void of space.
The consequences were just absolute devastation for any life on the surface. Without an atmosphere to stabilize the temperatures, surface pressure plummeted to just 1% of Earth's. Those brilliant oceans? They either vaporized into space or froze solid. Intense solar radiation began to relentlessly bombard the surface. If there were any tough-as-hell Martian microbes left, they had absolutely no choice but to retreat deep underground, hiding in aquifers or clinging to geothermal hotspots just to survive.
-60 degrees Celsius. That is the staggering, freezing average surface temperature of the modern, dry, and rusty Amazonian period we see today. It's a harsh, totally unforgiving environment where liquid surface water simply cannot exist for long. Any life that once swam in those warm chemical buffets of the Jezero crater has been gone or deeply buried for billions of years.
Bringing the samples home for the 2030 mission.
So look, we have incredibly compelling chemical clues, the vivianite, the greigite, those organic leopard spots, but we can't definitively prove they were left by microbes just by using the rover's cameras. To get absolute, undeniable proof that these leopard spots are microbial fossils, we have to physically get those exact rock cores back to Earth. NASA and the European Space Agency are orchestrating an incredibly complex robotic sample return mission for 2030. Now you might be asking, why not just send astronauts? Well, human beings are, quite frankly, just giant bags of microbes. Sending humans right now would easily contaminate the samples, completely ruining our search for unambiguous signs of alien life.
But while we wait for those pristine samples to arrive in 2031, here is a highly surprising fact for you. We actually already have over 400 pieces of space rock with verified Martian origins sitting right here in Earth's laboratories. How is that possible? Well, billions of years ago, massive asteroid impacts on Mars blasted chunks of the planet straight into space, and some of those rocks eventually crashed right here on our planet.
Which leads me to this totally wild, thought-provoking theory I want to leave you with today. If microbial life was common and thriving in the warm, watery lakes of Mars 3.5 billion years ago, and we know that chunks of Martian rock migrated here to Earth during that exact same period, could those rocks have carried primitive life with them? The ancestors of all life on Earth, including you and me, might just be from Mars. Are we the Martians we've been searching for? Definitely something to think about until our next explainer.